Alright, so the next periodic trend that we want to discuss is called electronegativity. So electronegativity is a measure of an atom's ability to attract electrons. Okay, so if you attract an electron to form an ion, you have a negative charge. Okay? So electronegativity is another way of saying how good is an atom at getting a negative charge. So if you think about the periodic table, you could probably guess this section right here would probably have a greater electronegativity than this section over here. Because this section over here has a negative charge when it forms an ion, so it likes to gain electrons. This section over here doesn't like to gain electrons. Okay, so we'll use this concept of electronegativity quite a bit in the next chapter when we discuss bonding. But for now, let's discuss the trends across the periodic table. So we'll abbreviate it capital E, capital N. Electronegativity increases. So we'll say as you move up and right across the periodic table. So I'll go ahead and make a note here. Electronegativity, so we'll abbreviate that EN, and the next periodic trend we'll discuss is ionization energy. They don't apply to noble gases. And so we'll just ignore noble gases for this. They typically don't attract electrons. So electronegativity increases as you move up and to the right across the periodic table. So if it increases up and it increases to the right, then fluorine would be the most electronegative element because it is the atom that is furthest right and up. It isn't a noble gas, okay? So we don't consider the noble gases in this. I'm trying to focus my camera. So now let's think about why this happens, okay? So let's talk about as you move up first. So as you move up a family or group, there are less energy levels. Okay? So think about what is really attracting electrons. It's the nucleus. The nucleus has a positive charge, so the nucleus is attracting that negative charge. So we know the concept of Z is the concept of a nuclear charge, so how positive a nucleus is. So now we have another concept. We'll abbreviate Z subscript EFF. So we call this the effective nuclear charge. Okay. So we can very easily find the nuclear charge. It's just the number of protons. Okay. So the effective nuclear charge is basically how much of an effect those protons have on something not in the atom. So that's kind of a difficult concept to think about without an example. So let's think about, let's just pretend we could somehow have two atoms and they each have 11 protons. Okay, so they're the same element here. And let's say the first atom had 2 energy levels. Okay? And the second atom only had 1 energy level. Okay, so 2 rings of electrons, 1 ring of electrons, for lack of a better way of saying it. And they both have the exact same nuclear charge, but this nucleus, if I put an electron halfway between these 2 atoms, this nucleus would be better at attracting this electron. Okay, it has a greater effective nuclear charge because there's less electrons blocking it. So that brings us to our next term, shielding. So shielding is when electrons, so we'll say our energy levels, block the nuclear charge and therefore lower effective nuclear charge. Okay? So we can say that there are more electrons or more energy levels shielding this nucleus than there are electrons shielding this nucleus. So this nucleus is more de-shielded, it has less shielding. So the less shielding you have, the greater nuclear charge you have. So let's look at an example of fluorine and chlorine. So fluorine has a nucleus, then it has 2 energy levels. Chlorine has a nucleus, and it has 3 energy levels. Okay? So chlorine, so this is Cl, this is F. So chlorine, we'll say chlorine's nucleus is more shielded by electrons, and we'll say energy levels as well. And therefore has a lower effective nuclear charge. Okay, so even though chlorine's nucleus has a greater positive charge than does fluorine's nucleus, because it's shielded, it has a lower effective nuclear charge. So its nucleus would have less effect on this electron halfway between it. Okay? So fluorine, let's say fluorine's nucleus, can better attract electrons. Okay? So because there are more energy levels shielding chlorine's nucleus, fluorine's nucleus can more easily attract the electron. So that is the reason for the trend up and down the periodic table. So let's think about the trend across the periodic table. Let's think about chlorine and sulfur. So sulfur and chlorine. Sulfur's nucleus has a plus 16 charge. Chlorine's nucleus has a plus 17 charge. Okay? Chlorine and sulfur both have 3 energy levels. 1, 2, 3. Okay? So energy levels don't play a role here. Okay? So shielding is approximately equal. Okay? So both these nuclei are being shielded by the same number of energy levels. So if shielding is the same, if the electrons blocking it are the same, what's better at attracting a negative charge? A plus 16 charge or a plus 17 charge? Yeah, a plus 17 charge. Okay? So if you're on the same period, the same row, all that matters is the actual Z, okay, the actual nuclear charge, because shielding is the same. Okay? So all we care about is the number of positive particles in the nucleus. Okay, so let's look at a few examples. Which has a greater, we'll say electronegativity. We'll just ask a couple and then we'll say why. So let's say bromine or selenium. Okay? So the correct answer here would be bromine, and it is because shielding is equal and the nuclear charge is greater in bromine. And then we could say bromine versus iodine. So here again, bromine would be greater. And this is because iodine has a more shielded nucleus. Okay? Therefore, a lower effective nuclear charge. You can write out effective nuclear charge, abbreviating that as ZEFF or ZEF is very common there. Okay? Or you could say kind of the opposite of that. Bromine's nucleus is less shielded and therefore has a greater effective nuclear charge.